Hello. Here we're going to look at when we're allowed to find a derivative. And this is for learning intention 11. So before some function f of x can have a derivative, it needs to satisfy some conditions. It needs to satisfy some rules. I'm going to go ahead and give you the statement, and then we're going to learn what the words mean. So when I write this statement, it won't make sense yet until we define each word. This is a conceptual video, so you're not going to be learning a procedure, you're going to be learning the meaning of words. So if you're wondering what you need to get out of this, it's not a procedure. When does the derivative exist? So for f of x, the derivative f dash of x exists when f of x is, and these are two important words, smooth, when it's smooth, and we have another important word, continuous. So we're allowed to find the derivative when we satisfy these two qualities. The best way to define them is to define what they're not. So let's start with continuous. So I'm going to draw a function that is discontinuous. I'm going to rule up some axes, and I'm going to draw a discontinuous function. So this means it's going to have some kind of jump or some kind of break in it. I'm going to fix that a bit. That's not quite straight. There we are. It's going to have a jump or a break, but it's still going to be a function. It's just not going to be continuous. Here's the function, and it stops there, and it resumes there, and it keeps going. Alright, is this a function? Well, it is a function because it passes our vertical line test. So any vertical line I draw through it passes through 1 point. So it's definitely a function, but it's discontinuous. Discontinuous. And you can see why, because it's going continuous, 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 continuous. It breaks, and if something breaks, it doesn't continue. So it's discontinuous. So we don't like that. It's not nice. We don't like that. Let's look at the word smooth. So I'm going to draw a function that's continuous. So this function is going to satisfy our first rule, but it's not going to satisfy our second rule, which is weird. So it's going to be continuous, but it won't be smooth. And this function I'm going to draw is called the absolute value function. So you know what this looks like. It looks something like this. Whoops. There we are. That's the absolute value function. Alright, so yeah, it's continuous. Look, there's no breaks, but at this point here, it has a corner, it has a cusp, it has a vertex. It's not smooth. It's quite sharp actually. It's literally not smooth. And that's what you're looking for. You're saying it's not smooth. We don't like that either. That's not smooth, because it's not smooth at 0, 0. Let's pretend this point is at x equals 1. So that's discontinuous, and that's not smooth. Well, what do we want? Well, we want a smooth continuous function for the derivative to exist. I'm telling you what I don't want and what we don't want. Let's look at what we do want. Let's draw a nice function that we like. So this function is going to be both smooth and continuous. Some examples of smooth continuous functions are parabolas. Cubics are smooth and continuous. Let's see, here we go. There's our f of x. Alright, is it smooth? Well, let's follow through. There are no cusps, there are no sharp points. So yeah, it passes the smooth test. We like the curve, smooth. Is it continuous? Alright, well, there's no breaks, so it's continuous. Beautiful. Well, we can say that because it passes the smooth and continuous test, we can say that f dash of x exists for all values of x. That's really nice. But hang on, all values of x. So what I'm saying is that the derivative exists for all values of x. So over here, well, the derivative doesn't exist, but if we wanted to find a derivative of this function, we could. It would just have to restrict the domain. So over here, we could say this is a function we could find the derivative for, but we'll need to chop out this point. So we'd have to say x is an element of R, not including 1. And we could find the derivative here, but couldn't include this point because the derivative doesn't exist there. So we'd have to say x is an element of R, not including 0. So we care about these conditions to the point where we'll restrict the domain to make it so we can get a derivative. So for f of x, the derivative f dash of x exists when that function is smooth and continuous. So if you know what the word smooth means, and you know what the word continuous means, you know how to check for them, and you know why we care, then you've gotten everything you need to know out of this video. And if you have been, thank you for watching.